Well, hello all. We are continuing with going through paper 1 questions from 2017 to 2020 paper. It's well worth going through the past questions because if you've been through them, you can be almost assured that when you write in 2021, you're going to get exactly the same questions. So let's start and have a look at the questions. So let's go to the 2020 paper. So this is question 10. An experiment is conducted to investigate the relationship between the frequency of light incident on a metal and the maximum kinetic energy of the emitted electrons from the surface of the metal. The experiment is conducted for 3 different metals, and here it's got energy. We always look when we got a graph, what's on the y-axis? It's kinetic energy, right? Not just any old energy, kinetic energy and frequency. So what do you need to know about this photoelectric effect? Well, you see, you got different metals, and each metal's got, say, the same frequency of light will affect different metals. For one metal, in this case potassium, the electrons will come off with a lot of kinetic energy. For another metal, so this is as the frequency increases, it takes a greater frequency even to get an electron of zinc, and then it takes the greatest, look how this frequency is rising, frequency of light to get an electron to come off platinum. So really, in this section, there's only one thing you really need to know, but I mean, it's got whole variety, and that is that energy is equal to Planck's constant times frequency. So energy equals frequency. So energy and frequency are equivalent, and the more frequency, the higher the frequency, the more the energy of these little balls. So you got these little balls, photons, they come and they bang into the surface of the metal and they knock off the photoelectrons. And depending on which metal you have, so the electrons will come off slowly off platinum, faster off zinc, and very fast off potassium, if I'm looking at this graph correctly. So name the phenomenon on which this experiment is based, the photoelectric effect. Name the physical quantity represented by X on the graph. So here we've got, say we extend this down to where it crosses, this is going to be the work function. Look, if you've got kinetic energy, and this is a graph of energy, take a guess. What's the minimum amount of energy? It's the work function. The minimum amount of energy needed to knock a photoelectron off the surface of the metal. Which one of the 3 metals needs incident light with the largest wavelength? They're always trying to catch us with wavelength. So a large wavelength means a low frequency. So they're asking which of the 3 metals needs light with the lowest frequency for the emission of electrons. So if we see here's the lowest frequency, and potassium needs the lowest frequency or the largest wavelength, then zinc, then platinum. So don't be fooled by, always think in terms of frequency rather than wavelength. Give a reason for your answer. Well, you can see that for the minimum, when the kinetic energy is 0, this frequency represents the threshold frequency, and the threshold frequency for potassium is lower than the threshold frequency for zinc, and platinum has the highest threshold frequency. So this is the frequency that is required to just get the electron to come off. Now, any extra frequency goes into increasing its kinetic energy. So it would be, because potassium has the lowest threshold frequency and the lowest work function. Define the term work function in words. The work function is the minimum energy required to to knock a photoelectron off the surface of the metal, calculate the work function of platinum. So if we go to our data sheet, let's find on our data sheet, see right here at the end, under wave sound, we've got energy equals work function plus EK max, and work function is equal to Planck's constant times the threshold frequency. So if we know the threshold frequency and we know Planck's constant, we can find out the work function. And Planck's constant is at the beginning here, h equals 6,63 times 10 to the minus 34. So if we go back here, how do we calculate the work function of platinum? We go and we read what is the threshold frequency, which is somewhere between 1.5 and 2. The exact middle is 1.75. We take 1.75 times 10 to the 15 hertz, and we say, what are they asking here? Calculate the work function. So work function is equal to Planck's constant, 6,67 times whatever, times the threshold frequency. So we use the formula we were at, and we work that out. The frequency of the incident light that will emit electrons from the surface with the maximum velocity of that. So there's your velocity in meters per second. And now we have to work backwards and find the frequency. So say we know the work function of platinum. Let's go back to our formula sheet. So under waves, we know the work function. The rest goes into kinetic energy. And the formula for kinetic energy is a half mv squared. And all of these are max. Always quote the correct formula. So if we know half mv squared, then we can put that into there. Let's just see if they give us a formula with that. Do they give us a formula? No, we've got to substitute in this. There's no formula that already comes with it, I don't think. So we say energy required is work function, which we've worked out, plus EK max. So let's work out the EK max using this formula. So we say half. We look up the mass of the electron. We look up the velocity of the electron. Let's find the mass of the electron, which is at the beginning here. There's the mass of an electron. So going back to this problem, we need the frequency of light, or the that will eject electrons with this velocity. So we take this velocity, we square it, we multiply it by half and m, which is the mass of the electron, and then we've got the energy which this electron will have. To that we add the work function, and that gives us the total energy that is required, and then we turn that energy into a frequency using energy equals HF. I've got the memo here because that sounds really complicated, so let's just see. So there's E equals work function plus EK max. We've worked out the work function. So then we have the half, there's the mass of the electron, there's the velocity that they give us, squared equals Planck's constant times frequency. And so there's the frequency that we finally have. So we take HF, H Planck's constant times the frequency you're trying to find, equals the work function plus the half, the mass of the electron times the velocity of the electron that they give us, the photoelectron. And from that, the only thing we're left to find is F, and it comes to that answer. Okay, so let's go to the 2019 paper. During an experiment, light of different frequencies is radiated onto a silver cathode. Okay, so we've only got one metal in this case of a photocell, and the corresponding maximum speed of the ejected photoelectrons are measured. A graph of the energy of the incident photoelectrons versus the square of the maximum speed of the ejected photoelectrons are shown below. Okay, what is horrible about this is you've got energy of the photons. So this is as the energy cranks up of the photons. So the velocity of our photoelectron squared it's not nice to have the squared here. That's always going to frighten some people. So, but anyway, think of it in terms of this V squared represents the kinetic energy. So at this point here, there's no kinetic energy at this energy of the photons. So this must be the threshold frequency. The work function, the minimum amount of energy where you get no kinetic energy. Look, there's V, half mv squared, which is the kinetic energy, is naught. So here's your work function. And then as the energy of the photons creeps up, meaning the frequency creeps up, and there's a certain point where the energy's reached a certain amount, and then they're going to have a question regarding X. Okay, define the photoelectric effect. The photoelectric effect is, what is the photoelectric effect? The photoelectric effect is where a photon of light falls on the surface of a metal and causes a photoelectron to be ejected from the surface of that metal. So it is when a photon of light strikes the surface of a metal, it causes an electron called a photoelectron to be emitted from the surface of the metal. Look up your definitions. Write down the value of the work function for silver. Use a relevant equation. Like I said, this is the minimum amount of energy the photon has to have no kinetic energy. Just think of V squared as the kinetic energy. Half mv squared is the kinetic energy. So here's no V squared, meaning it's got no velocity, it's got no kinetic energy. So that answer is our work function. Use a relevant equation. So let's go back to our equations for waves. So we know the energy is when our work function is 0. Here's our energy equals work function plus kinetic energy. So when our kinetic energy is 0, our energy of the photoelectron is just equal to the work function. So when our energy of the photon is equal to the work function, we have no kinetic energy. And that's the case at where we had that 7.48. So we're going to use that equation. Which physical quantity can be determined from the gradient of the graph? Okay, let's just go back again to that. Look, we've got energy is equal to work function plus kinetic energy. So if you think of it, the energy, ignoring the work function, is equal to the half mv squared. So if we take the energy, which is, and we divide it by the v squared, we're left with a half m. And so the answer is actually m, or half m, but they would only give you a half mark, I think, for, say, including the half. I don't know why. But energy divided by the velocity squared, energy, if you ignore the work function, divided by the half m, divided v squared. If you divide that by v squared, you're left with m. So the answer is the mass of the electron. That's the gradient of the graph. Calculate the value of x as shown on the graph. So here we have a certain, we've got to calculate the velocity if we have that amount of energy. So it looks like here's your work function, all of the rest of this. So if you subtract that from that, and don't forget to use those times 10 to the minus 19, that minus that, the difference, all of that goes into a half mv squared. And they're asking you to calculate the v squared. So you're going to take whatever that amount of energy is, and you're going to turn it into a half times the mass of the electron times v squared. And then you're going to be able to find out v squared by that difference divided by half, and m will give you v squared. So you're going to do that to calculate x. Let's just see. I think I have the memo, and that question was 10.4. So let's just have a look at 10.4. So the gradient of the graph is equal to half m. And there's the m. And they've subtracted the two energies. And there's your x-axis. So there's your gradient, which is the two energies. That's the y-axis. There's your x-axis to find x equals a half, and the mass of it. So when you divide the difference by a half and the mass of the electron, you're going to get your v squared. So there's the answer for x, or v squared. So let's go back to this question. The experiment now above is now repeated using light of a higher intensity. How will each of the following be affected? Choose increase or remain the same. So does the speed of the electron change as we increase the intensity? That means we have more electrons strike the metal. Does it change the energy profile of the electrons? No. But it will. So this would be remain the same. The gradient will remain the same, but the number of photoelectrons emitted will increase. So we must always remember that the velocity doesn't change as we increase the intensity, but the number of electrons will increase. However, if we had a higher frequency of light, what it does is that higher frequency actually represents the amount of energy here, the energy of the photons. So there's the answer to that question. Let's go to the next year, which is 2018. The threshold frequencies of cesium and potassium metals are given at the table below. There's cesium. Notice it's got its frequency in hertz. Potassium's got a higher frequency. Notice times 10 to the 14. So it means the threshold frequency is the minimum frequency for a photoelectron to get bumped off. So potassium requires more frequency, which means more energy to knock off an electron. Define the term work function in words: the minimum amount of energy required for a photon to knock a photoelectron off the surface of a metal. Which one of the two metals in the table has the higher work function? So which of these requires a higher frequency to knock the electron off? And that would be potassium. Give a reason for the answer by referring to the information on the table. So we will say potassium has a higher threshold frequency, therefore it has a higher work function. Now, a simplified diagram below shows two circuits A and B containing photocells. Photocell A contains cesium. Remember, that's easier to knock electrons off. And then potassium, it's harder to knock electrons. Both of them have got ultraviolet light striking them. And then it says ultraviolet light with the same intensity and wavelength. There they give the wavelength. Now, the moment you see wavelength, convert it to a frequency. Honestly, save yourself a whole lot of work, because we don't like to work in wavelength in any place. So let's just go to here's how we're going to convert it. Velocity or sound speed of light equals frequency times wavelength. And they give you the wavelength. We can find the velocity of light, which is otherwise known as c. And here c is given us. There's the speed of light, 3 times 10 to the 8. So we're going to go and immediately I would put 3 times 10 to the 8 there. Put the wavelength they give us and convert it to a frequency. Just make your life so much simpler. Okay, So now we have, say we have a frequency here of the ultraviolet light is incident on the metal plate in each of the photocells, and the ammeter in circuit A registers a current. So we know that this frequency must be above that frequency for the cesium to register a current. Okay, so that frequency, whatever you worked it out to be, is enough, high enough to knock photoelectrons off the cesium metal plate surface. Now determine whether ammeter in B will also register current. So say you've converted that to a frequency. And if that frequency is higher than 5,55 times 10 to the 14, then it will have a current. And if it's lower, it won't have a current. So whatever the frequency is that you converted this to, if it's higher than this value, then there will be a current. If it's lower than this value, it won't have a current. So all you had to do is change this to a frequency and then compare the frequencies. Calculate the maximum kinetic energy of an ejected electron in circuit A. 5 marks. Okay, so suppose we now know the frequency, we worked out the frequency of this ultraviolet light. We multiply it by Planck's constant and we get E equals HF. So now we know the E, the energy of this light. And then we go to this formula. So now we know the energy, which is equal to HF. Okay, it's there, it sits. We know E is also equal to the work function plus the kinetic energy. So if we now know the E, we can work out the work function by taking how much energy it takes to just knock it off by saying H times the threshold frequency. See, work function is H times the threshold frequency. So he again takes Planck constant multiplied by the threshold frequency of cesium, and then we get this work function. Then we subtract that from E, and all the rest goes into a half mv squared, or the velocity of the electrons. So so that is what we're going to do. Then all that extra energy is going to go into half mv squared. So we say we've worked out that energy, so we've then look up the mass of the electron, and that's the way that we'll be able. Oh, well, we don't actually even have to work out the mass of the electron. All that extra energy, once we subtract the work function from this frequency times Planck's constant, and that will leave us, all the remaining energy will go into the ejected electron. So that's all we have to do. Take that frequency, multiply it by H, and subtract it from it, this frequency times H, and all the rest will be the energy of this. How will the maximum kinetic energy of the ejected electron calculated in question 11.4 change when the intensity of the light? Remember, we said intensity only leads to more electrons being, it doesn't lead to greater kinetic energy, so it will stay the same. How will the maximum kinetic energy of the change if the intensity, it stays the same? The kinetic energy stays the same, so there's just more photoelectrons, so they don't ask that. And then the last paper, I'm not sure we still do this. So I'm just going to skip down. This is 2017. We do have this where you have your, you remember your Aufbau, you have your ground state, and then you get higher energy levels. And when electrons go to an excited state and then fall back to the ground state, they give off energy, and that goes into the photons. So if you take this value and subtract it from the ground state, that's how much energy goes into the photon. Or if you take this value in joules and subtract from it this, that amount of energy goes into the photons. Okay, Do the transitions indicated in the diagram lead to an absorption or emission spectrum? This is a hot gas. The electrons have been excited and now they're falling back. So that is an emission spectrum. Calculate the frequency of the photon produced when an electron makes a transition from E4 to E2. So you take that amount of energy, subtract that, and now you've got a certain amount of energy. And energy is equal to Planck's constant times frequency. So if you know the energy, you know Planck's constants on your data sheet, you can therefore work out the frequency of that photoelectron. Then it says the threshold frequency of a metal is this. Calculate the kinetic energy of the most energetic electron excited when the photon produced in question 1122 is incident on the surface of the metal. So if we knew the amount of energy and we know the threshold frequency, if we know the threshold frequency, you multiply by Planck's constant and we get the work function. We subtract the work function from this amount of energy of the photon. So the photon's got a certain amount of energy. The threshold frequency changed into energy by multiplying it by Planck's constant gives us the work function. Subtract the work function from this amount of energy, and all the rest goes into kinetic energy. So that's how we calculate the kinetic energy here. Excuse me. Now it says another metal has a higher threshold frequency of 7,5 instead of 4,4. So this requires more energy for it to be knocked off. Will the photon produced in question 1122 be able to eject electrons from the surface of the metal? Write yes or only yes or no. Give a reason for your answer. So it says another metal with a threshold frequency higher. Will the photon produced in question, this photon here, be able to eject electrons from the surface of the metal R? Huh. This 2017 paper was quite challenging. Calculate the frequency of a photon produced when the electron in an excite. Look at what I'm thinking of doing is if I take this, this, multiplied by Planck's constant, I get a certain amount of energy. I compare it with the difference between there and there, and I see if this energy, that times Planck's constant, equals that energy difference, which is 2,044 minus 1,635. And then if this is higher than that, then there will be no electron ejected. So I guess one would have to work it out. But it sounds like they almost expect you to be able to work it out just from mental arithmetic. But that's what I would do. And then you would get your answer. That's about the best I can do for that 2017. But one could definitely know that times Planck's constant is a greater or lesser than that minus that. Greater, if this is greater, then it will not be able to. And then they say write down only yes or no. Yeah, and give a reason. Well, because this threshold frequency times Planck's constant will give us the work function. And is this work function greater or less than this value, which you've already calculated? And if it is greater than, then no electron will be emitted. Okay, so there we go. We've finished with our photoelectric effect. So let's finish this then.